Now we've looked at what it means for a relation to be reflexive. The next two properties we're looking at is when a relation is symmetric and transitive. So let's look at symmetry first. A relation is symmetric if and only if ARB implies BRA. So if I know ARB is true, then BRA is true, then my relation is symmetric. So let's start with the example we ended off with the previous video. We tested this relation P for reflexivity, and we saw it was reflexive. Now let's see, is it symmetric? All right, so now we know what this relation does. A minus B is divisible by 3, then APB is true. So if I want to test for symmetry, I'm given ARB, I must show. So this part is given, and this is the part I want to show. If I suspect it's symmetric, then I've got to do it in general for any A and B. If I think it's not symmetric, then I need one counterexample to prove it wrong. So this one, let's take a look. Given ARB, so we know ARB is true, then what do we know? This is P. Given APB, then A minus B is divisible by 3. So 3 is a divisor of A minus B. What does that mean? There exists some integer k such that A minus B is equal to 3k. So that's what this means. All right. Now what do I want? I want to show that BPA is true. Well, BPA will be true if B minus A is 3 times some integer. Now we can see what's happening here. If I multiply this side with a minus, and I multiply this side with a minus, everything stays the same. But minus A plus B is the same as B minus A. Minus 3k is the same as 3 times minus k. Now I know k is an integer. Therefore, minus k also has to be an integer. So therefore, 3 is a divisor of b minus a, since minus k is an integer. So if 3 is a divisor of b minus a, then I know BPA is true. So therefore, P is symmetric. All right, so this one relation we've already shown is reflexive. Now we've shown it's symmetric. All right, let's look at the next two. We also looked at them. The first one we saw is reflexive. The second one was not reflexive. But let's look at symmetry. All right, so the question is if this relation R is defined as ARB if and only if A is equal to B. So we want to show that it's symmetric. So if I've got ARB, I want to show that BRA will also be true. But it's so simple. ARB is only true because A is equal to B. Well, if A is equal to B, then B is equal to A. So therefore BRA. So therefore R is symmetric. So this relation will still work if I swap the A and the B. So let's look at the next one. APB. Well, if A plus B is less than 6, will B plus A be less than 6? Well, we know addition is commutative. So this one, if I'm given ARB, is it P? APB, I forget what I name these relations. APB, then I know A plus B is less than 6. But if A plus B is less than 6, then B plus A is less than 6. So therefore B, PA. So I've shown that P is symmetric. So I can swap them around. All right, but now remember, to show that it's symmetric, it's better to show it in general. If I've got a small set, I can test each and every one combination, but it's going to get too messy and there's too much to do. So if you want to show a relation is symmetric, you do it in general. So let's look at the next one. Is this one also going to be symmetric? It seems like we've got 3 that are symmetric up to now. What about this one? A minus B is greater than 10. Well, A minus B is greater than 10. Will B minus A then be greater than 10? That's what we're asking. Now we know how minus works. This doesn't seem like it's going to work because 20 R5 is true. Since 20 minus 5 is 15, and 15 is greater than 10. So I'm happy with that. But then what about 5R20? Is that going to be true? No, because 5 minus 20 is minus 15, and that's definitely not greater than 10. So here I used one counterexample. There are an infinite number of counterexamples you can come up with. We just need one. So 20R5, 5R20 doesn't work. So 20R5 is true, 5R20 is not true. So that means that R is not symmetric. Now, we didn't test this example for reflexivity, but will ARA be true for all A's? So will A minus A always be greater than 10? Definitely not, because A minus A is 0, so it'll never be greater than 10. So this one is not reflexive either, but we're looking at symmetric now. So reflexivity we've looked at symmetry. Let's look at transitive. When will a relation be transitive? So this is the third one. We test if it's reflexive, if it's symmetric, if it's transitive. Now, if a relation is all three of those, then it's special. So we'll get to that in the next video, but let's take a look. A relation is transitive if ARB is true and BRC is true. Then I've got ARC is true. All right. So let's look at the divisibility example. We've already shown that it's reflexive and it's symmetric. So is it transitive? Let's take a look. I'm going to show it in general. If I come up with a problem, then I can look for a counterexample, but let's just start. So we're given those two, and this is what we want to show. So let's get started. Given APB and BPC. This is what I'm given. I want to show APC. So let's take a look. If I'm given those two, then I know A minus B is equal to 3 times sum K. Now, I'm going to come back to this one. I'm going to change this shortly. And B minus C is equal to 3 times sum K. These K's are not the same necessarily, so I must distinguish between them. I need two different K's. K1 is an integer and K2 is an integer. So please do not use the same K, because if you have just got a K and a K, that means it's the same K. So I distinguish them with subscripts, K1, K2. So they're both integers. So that I know it's true. So what am I looking at? I want to show that APC. So I want to link A and C. Well, if I just add those two equations together, A minus B plus B minus C is equal to 3K1 plus 3K2. The B's cancel out, and I've got A minus C. That's where I wanted to get to. Well, A minus C, can I show that it's 3 times some integer? Yes, and I know that K1 plus K2 is also an integer, because the integers are closed under addition. So I can write A minus C as a multiple of 3. So A minus C is divisible by 3. So therefore I've shown APC. So therefore P is transitive. So to show that it's transitive, we have to look at it in general for A, B, and C elements of Z. And I need to show APC in this case. All right, so let's look at these two examples. Yes, again, we're going to look at them in general or have a counterexample if it doesn't work. So let's look at the first one. So the first one, when A is equal to B. Well, this is also it's a very trivial example. So if we're given A are B and B are C, then I know A is equal to B and B is equal to C. So then I can conclude that A is equal to C. So then A R C. So R is transitive. All right, the next one, if A plus B is less than 6. All right, now I've got to think a little bit. Now I'm adding numbers together. So if I'm given APB, so A plus B is less than 6, B plus C is less than 6, does that mean A plus C is going to be less than 6? Let's just write that down and see if it looks like it's going to work. Given APB and B, P, C. Then we've got A plus B is less than 6. B plus C is less than 6. Does that mean that A plus C must be less than 6? When I start adding things together, that doesn't look like it's going to work. Let's see, because what happens if B is a little number and A and C are both big numbers? So if B is 1 and 1, if B is 1, then I can maybe have 3 plus 1. So 3P1 is true, because 3 plus 1 is less than 6. And 1 plus 4 is less than 6. But I know 3P4 is not true, since 3 plus 4 is not less than 6. All right, so this P is not transitive. So from here, we're going to look at relations that have all three of these properties. So we're looking at reflexive, symmetric, and transitive.